Hello, everyone. Welcome to the fifth rerun of our course, Introduction to Quantum Computing, Quantum Algorithms, and Qiskit. I'm Dr. Anupama Ray. I'm a senior research scientist at IBM Research India. I'm also the technical lead for AI for Quantum for IBM Quantum. Welcome you all to this course. And today, what we really want to discuss in this video, which is ungraded, is what is it that we are wanting to do in quantum and why is this all about? Why are we learning quantum today? What is the potential impact? Potential impact is quite near term in terms of making compute industrially relevant. So, what is it that we want to do in quantum computing? We want to go towards quantum advantage. In the center of your screen here, you see this white circle. These are classically easy problems. For example, sending an email or doing a video conferencing are many such problems which are easily solved by classical computing or by AI. But there exists a wide number of problems in this gray ellipse that cannot be solved by classical or even AI supercomputing and never will be. A part of those problems are quantum easy and can be solved by quantum. And what is most interesting to me is this new section of problems, which we were earlier not able to touch or not able to think. These are quantum easy problems, which we were unable to do using classical computing. So, in all of data driven sciences, there is a rich seam of problems that we will able to try or we will able to design or solve via quantum computing that is intractable to classical computing. A lot of people ask, when will this happen? I would say it has actually started. Organizations across industry and fields are accelerating their investment in quantum computing with an unprecedented pace. If you look at this graph, you'll see that the number of active POCs by different industry and the industry sectors are color coded here. That has been increasing. And in the last 3 years, it has increased over 50% in the enterprise use case activities in quantum POCs. Investment in quantum computing is accelerating worldwide. There's a lot of global investment. For example, in 2018, the National Quantum Initiative Act authorized 1.2 billion investment in funding over 5 years in the US. In 2019, France formalized the French quantum strategy with a budget of 1.8 billion euros over the course of 4 years. In 2023, Germany released its quantum technology plan, investing 3.3 billion euros towards the development of a universal quantum computer by 2026 in an effort to build a quantum ecosystem and a quantum industry. And the list goes on with Australia and so many other countries, everyone creating Japan, everyone creating their own quantum plan. And so does India. India announced its national quantum mission in the finance budget in 2020 for the first time. Then there was a sanction of 60 billion, which is an investment over the course of 8 years from 2023 to 2031. And we have multiple goals that we are trying to achieve. India should definitely have its own quantum computer. So the first thing, building the quantum computer, a 50 to 1000 qubit machine built on any technology, but that needs to be built. In quantum communications, we want to have an intercity QKD over 2000 kilometers. In quantum sensing, we want to be able to develop high sensitivity sensors and materials. For this effort, we have been creating these hubs at 4 different places in India and working actively. The next goal, which is workforce development, and that is part of what we are doing here. India has to produce 100,000 people who are trained quantum developers by 2030. In our course itself, in the last 4 runs, we have skilled 37,000 people. This year, we have more than 50,000 people who have already registered for this course. In terms of number of startups, we currently have 60 plus startups in India already, a large number of them here in Bangalore. And the states have been very supportive. For example, Andhra Pradesh government has already called out and supported that they are going to support 100 plus startups and so on in other states. And the target here is to have 200 startups by 2030. There's a large number of research papers that are using these type of hardwares and softwares produced by different quantum vendors. Of course, as a result, research in quantum computing is proliferating, with IBM leading in quantum hardware and software. And since 2016, when we first made our quantum computer accessible via the cloud, the scientific community has leveraged our quantum technology, making groundbreaking advances in their fields, publishing several papers. And we have over 5,000 papers that we have been able to publish on our hardware. And of course, using our software. When we think about what constitutes a useful quantum computing, there are three key milestones to us. Quantum utility, and we were able to establish quantum utility in 2023. What do we mean by quantum utility? We were able to run these quantum experiments reliably, multiple times, repetitively. We get the same results across different hardware at different noise levels, which are better than classical brute force mechanisms. In 2026, we are looking forward to be able to demonstrate quantum advantage along with our partners. And in 2029, we have already put that in our roadmap. We'll be delivering a first large-scale quantum fault-tolerant quantum computer. But why do we say we shouldn't wait for fault tolerance? Understanding noise is critically important. It helps us build better error mitigation algorithms and better error correction algorithm. And fault tolerance actually doesn't mean that there would be noiseless quantum computers. It still will have some noise. It's just that there is some fixed error budget. The noise thresholds are low, and real time we'll be able to correct those errors. Now, in order to build those correcting algorithms, we need to start now. So if we start now, then we'll be able to expand our error handling capabilities and create better fault tolerant quantum algorithms once the fault tolerant quantum computers are built. I'll just show you two graphs on the usage of these devices. Couple of years ago, people on an average were, I mean, the best number of qubits you would see is less than 100. Now it has gone to over 155 or 150 plus number of qubits people are actually using. So people are starting to use more number of qubits, starting to build these utility scale experiments with different algorithmic approaches, of course. And this graph on the right stands for the circuit sizes. That is, what is the largest circuit size that people are being able to run? So that impacts the number of gates and the circuit depth. And if you see, there are very, very deep circuits, more than 8,000 gates that are being, 8,002 qubit gates. So very deep circuits that are being able to run reliably on these hardwares. We are already seeing first claims of quantum advantages as researchers and developers run these circuits that test the limit of classical computing. We see these as hypotheses of quantum advantage. And this work is setting the stage, for the back and forth from which true quantum advantages will emerge. We see two parallel paths. One is an empirical test of quantum usefulness, which is, for example, it's a top-down approach where quantum scientists and quantum developers are applying heuristic methods that work well for real-world problems. And these explorations will help us realize quantum advantage for practical problems sooner. For example, the HSBC work where they are showing a 34% improvement in prediction of closing of a bond price. There's a 34% improvement with the quantum algorithm, and this has been rigorously tested over a couple of months across different hardwares on the same hardware at different times of the day and different multiple days across a few months and on different hardware. And you have consistently got an average of 34% improvement over the state of art classical algorithms. So that proves that empirically or experimentally, it proves that, okay, this particular advantage is definite, this particular algorithm definitely has an advantage over the classical algorithms. Similarly, we have got very good results from some of the work with Cleveland Clinic, with Moderna on the mRNA problem, with Vanguard, and so on. The second path that you see here is, while we are empirically coming up with these advantages, it is important to build trust in the quantum computers and the quantum algorithms that it is truly doing something beyond classical. We need to be able to identify the kind of quantum circuits that we'll be building that can offer a verifiable advantage. So, there is a lot of work where people are trying to come up with this rigorous proof of advantage. And there's a bunch of papers that I've listed here, but there's a lot more that is coming. And in order to track all this, we have created a community-run tool alongside Flatiron, Blue Qubit, and Algorithmic Q for the moment. But yes, we welcome more partners, and we are soon going to have a lot more partners. We want to be able to have this tool to track progress towards quantum advantage. So people like us, users, we can systematically monitor and evaluate verified demonstration of quantum advantage. You can submit your results here. You can put, okay, this is my circuit, this is the best result that I got, this was the classical resource, this is the quantum resource, and let people see how they can try to get better at it. So this particular tracker shows how these candidates stack up against the leading classical methods. Now, because people talk a lot about fault tolerance and all this buzz, it is hard to know what these words really mean. So let's break it down. First word people say what is large scale. So what is large scale? Large scale is hundreds of qubits capable of running hundreds of millions of gates. So that is the scale which we call large scale, right? That has to be the scale beyond, that is the scale where you cannot do classical simulation. And now you want to be able to run circuits 1,000 times deeper than what is possible on the devices today. The way we are going to get there is quantum error detection. And in this course, we are going to delve in the fourth week a bit into error correcting code and error detection. These are basically a set of techniques using error correcting codes to encode quantum information, not into one physical qubits, but into a number of physical qubits. And there are several ways to do it. A lot of people are simply taking 2 or 3 physical qubits and doing a parity check between them to detect errors. That won't get you to hundreds of millions of gates. If you're only detecting errors, the overhead, of course, is exponential. But the same stands for error mitigation. If you want to run that many gates, you will still need ridiculously good physical qubits, and you need to run the circuit billions of times to get the correct answer. In fault tolerant computation, you'll correct the errors in real time as they occur. Okay. So fault tolerance is all about this computing capabilities. And when we talk about computing capabilities, I really want to bring this to your attention. If you are running some quantum experiments with 10 qubits, you can run it on your classical computer. So whatever you're doing a quantum experiment which you're simulating on your classical computer, you can run it, and you will not get any potential advantage, because for 10 qubits you only need some small amount of 16K RAM, right? For 30 qubits, a modern laptop with 17 GB RAM will be enough. You can use your entire RAM, and you can still do somewhere around 20 to 30 qubit kind of experiments. But this is exponential. And so for 31 qubits, you will start to need 2 laptops. And very quickly things will get crazy. This is why, using classical computers to run quantum problems is actually a dead end. So IBM Summit is world's one of the most powerful supercomputer. And if you are running something around 48 qubits or 49 qubits, you'll need something like Summit. You want to run something at a scale of 60 qubits? What 60 qubits can do if you want to run that on a classical device? You will want to have all classical computers on the earth connected. So one big device, all atoms you want to exhaust. What you get to do is what you will be able to do via means of 60 qubits. And that is the example, that's a standard example of caffeine that a lot of people would give. That okay, caffeine needs around 64 qubits. For that, you need all atoms in the world and so on. And at 100 qubits, you would need a supercomputer about 10 trillion times larger than the frontier to represent its states. So this is a dead end. That's the reason why we say that okay, you cannot use classical computers to run quantum problems or quantum algorithms or quantum circuits. Now, this particular chart is very interesting to me. So on your y-axis is the circuit width or the number of qubits, and on your x-axis is the circuit gate size or the number of gates. And if you see, Starling is here, so it's the fault-tolerant quantum computer which is coming here in 2029. And Blue Jay, of course, is a very large one that's in 2020, 2033. And Blue Jay is the one which is actually, you say that that's the realm of, say, actual chemistry advantage or for Shor's algorithm and the best quantum optimizations and so on. Now, this going by this assumption, you should be able to actually see that advantage in 2033. And that has an assumption that your algorithms are not going to get anything better, only your hardware will get better and better, and then potentially you can be here. But that's not true. Algorithms are going to get better, right? So algorithm will definitely get better and hardware will also get better. So this advantage point is not going to happen in 2033, but it's going to happen way earlier. Somewhere around 2026 is what we had predicted that we will be able to see these advantages, but we are already seeing a lot of these advantage use cases. So that means in 2029, we'll be delivering the world's first large scale fault tolerant quantum computer, which we call Starling. So today, if you see, this is the IBM Quantum System 2. This is the one that is coming to India in the next 6 months. And this is Starling. What you will finally see as Blue Jay will look something like this, which will have, say, 2000 logical qubits or 1 billion quantum gates can be successfully run in this system. We have been very clear about our roadmap, and I'll just present very briefly to all of you the roadmap that we have articulated. We have a development roadmap and an innovation roadmap. And this is our development roadmap. So on the bottom layer, you see the hardware, which is in black. This is the kind of hardware that we have been putting out. We had put our first quantum computer available for anyone to access around the world in 2016. And it was a 4 qubits, very small machine. From that, we went on to 20 qubits, 53 qubits. We have a bunch of devices, and recently we have released something which we call Nighthawk. It's a 120 qubit square lattice. It's a beautiful device which is being able to do things way better than the 156 qubits can do. On top of that layer is something called Qiskit runtime, which is how can I accurately and efficiently run my quantum circuits on this hardware? So it is very closely tied to the hardware. On top of that, you have a set of tools which we call as orchestration tools, which helps us in doing resource management. For example, Qiskit serverless, plugins for HPC so that we can envision and work our plans around quantum-centric supercomputing. And then on top of that is the actual algorithm discovery. We have a bunch of algorithms that we build on top of it. Finally, that gets into our algorithmic researchers who do not have to, or our application people who do not need to understand everything in the stack below to be able to run these libraries. So this is Nighthawk. Nighthawk is a square lattice. Earlier we had heavy hex lattice. This is a square lattice. This supports more efficient circuits with fewer gates. It has a way better, information routing, and we are planning to scale even Nighthawk significantly. So it would be with the help of connecting these chips. Each chip has 120 qubits, but these chips will be connected by means of classical communication and quantum communication, and then we can actually stack them to 1000 qubits. And of course, then finally, we'll debut Starling, which will be able to run circuits with 100 million gates on 200 qubits, and then Blue Jay, which can run 2000 qubits very reliably. Now, this has been the next layers where you see there is a lot of focus on orchestration of workloads, quantum-centric supercomputing, then our resource management, and of course discovery and new algorithms which will lead to quantum advantage, and then finally applying those algorithms for applications. This is our innovation roadmap, which has all the details of what we have been doing. And one point that I really want to mention here is you will see a lot of people asking, what is the number of qubits? What is the number of qubits? Next time people ask you or think, okay, a better quantum computer is which has the higher number of qubits. Do keep it in mind. Scale is important, but reliability is even more important. So what we did, as I said, we had started with 4 qubits in 2016 that we had put out for everyone. And then we went out and we kept discovering bigger and bigger systems. Osprey in 2022 is a 433 qubit system. And then when we went to Condor, we had a 1124 qubit system. So we know how to scale. We can pack in more and more qubits in the same chip. You will ask me, why are you now going down to 120 qubits, much smaller than 1100? The reason is 1100 qubits with more noise is not as good as 120 qubits with more connectivity and significantly lesser noise. Then, if I can have each of these chips with significantly lesser noise and then connect them via means of quantum connections to other chips and increase my stack, increase my number of qubits, and have a very reliable execution of quantum circuits, that should be the way to go. So, scale is important, but scale is not the only parameter. You have to consider performance, which is speed of execution, and reliability, which is how good your execution is, which is how low your error is. So next time anyone tells you that, okay, how many qubits and how many qubits, please ask them that, okay, how many qubits and what is the error rate per qubit? What is the error rate of each connection? What is the performance? What is the speed? So that is very important when we look at hardware innovation. Of course, on top of that, we have been doing a number of things in software innovation. For example, our software toolkit, Qiskit, has been something which has constantly been evolving. In this course, we'll give a sneak peek to Qiskit. We have been building a lot of application modules now. In order to make Qiskit leaner, we have put these application modules separately out of Qiskit, and they are in Qiskit ecosystem. We, of course, have something which we call Qiskit runtime. This is a performance abstraction which directly works with the hardware on how can we run these circuits better on the hardware. Then we have something which we call quantum serverless, which is how can I manage quantum and classical computes on different computing and have this workflow orchestration. We have a lot of work which we do under the pillar we call AI enhanced quantum, wherein things like can I build better transpilation strategies for my quantum circuits using some AI algorithm. And we have been using classical reinforcement learning to come up with better circuit transpilation algorithm. Or can I actually have something like Qiskit code generation via means of using AI? There's a lot of work in terms of HPC quantum integration, and one major thing is we now have Qiskit C API, which can help you run things on C++ and C, which is something critical for the HPC community. We also have a lot of work in the advantages of finding the potential circuits that will have quantum advantage. And of course, we demonstrated a real-time error correction decoder, which is ahead of time. And I'm very proud of the team that they actually achieved it, which is something that we had targeted by end of 2026, but we have already achieved it. So we have whatever the roadmap you see is something that we have already achieved. And with that, I'll take a break and jump into the next topic, which is something very critically important for all students, and students keep asking us at every place that we go. That we study these courses, or you tell us to study a set of other courses after this introductory course. But what do we study this for? What are the careers there? And in one of my keynotes that I was doing, I had to prepare what are the careers in quantum computing. And I thought I'll use this to give you guys some motivation on why you are here and what are you preparing yourself for. But before we look at what are the career roles, let's also delve some time into thinking what are the areas of research in quantum computing and what are the career roles in each of these areas. Of course, we'll talk about the India story and the specific opportunities that India has. So going by the same roadmap idea, on the bottom I have the quantum hardware. And there are a number of research areas. For example, quantum technologies, like you want to be able to have superconducting as your quantum hardware, or photons or cold atoms or so on. You want to be able to do material discovery on what is the kind of materials that I would use for building my quantum hardware part and development. There's a lot of work in cryogenics, in calibration, in control system, chip design, in semicon fabrication, and of course, calibrating these devices. Then there's a lot of work in how can I build better architecture for efficient and accurate execution of quantum circuits on this hardware. There's if you are even a cloud expert, right, or you have been doing things in cloud, you can bring that knowledge into quantum, and you can see how you can orchestrate, and in this space of quantum centric supercomputing, how your knowledge on cloud or AI will be very, very useful in orchestrating workloads, in able to do things which you cannot do with any of these systems alone, be it quantum or classical. Of course, there's a ton of work to do in terms of discovering new quantum algorithms, be it in the space of simulation, optimization, quantum machine learning, or error correction, and so on. And then finally is the applications. If you can build these algorithms, and how can you solve some very important problems, say in high energy particle physics, or in chemistry, or in biology, or in finance, or and so on. How can you start from those complex problems in the application space? What kind of algorithms can you map there, and how can you get a benefit on those particular applications is actually going to determine your quantum advantage roadmap. So, the research or the engineering roles that we have here, of course, quantum hardware engineer, microwave engineer, cryogenic engineer, or clean room specialist, and so on. Their list is endless. And there are very few people who are skilled enough to do work in quantum hardware, not just in India, but across the world. This is a skill which is very rare. There is more skills or more availability of people in the space of quantum software research, but yes, that is something that is also more needed, and there are a wide number of places that if you are a quantum software developer or quantum software engineer or researcher, you can actually fit in yourself in all the layers above the last layer. So there's a lot of work in terms of quantum and cloud researchers in the orchestrating layer. Of course, the algorithms discovery needs a quantum research scientist or an algorithm researcher, whatever is the name in different industries. They are different names, but yeah, to me, both these roles are encompassing the similar type of work. And finally, a quantum scientist or a quantum research scientist, again, different names to the same designation, are the people who are looking at these applications. There is another business role, which is more of an industry consultant. There is a lot of roles in BD, sales, even in journalism about technical writing and so on, which cut across or cut through all the layers and are possible. They need a bit of technical along with whatever other role that they encompass. Now, of course, as I said, there are so many other roles. There's a lot of enablement required, so a lot of teaching activities required. So there would be need for more professors and teachers in this space, for client support, sales, BDE, for quantum product manager, and so on. So there's a lot of such other roles which would need some amount of technical knowledge, but which are not technically heavy, or they are not developers or research scientist roles. Now, coming to the India story. So, as I said, India announced its national quantum mission, and there's a lot of investment happening. So, Indian government has created four centers. So, the Quantum Computing Center is in IISc Bangalore, the Quantum Sensing Center is in IIT Bombay, the Quantum Communication Center is IIT Madras, and the Quantum Materials and Devices is by IIT Delhi. And then there are a large number of other institutions who are involved in these particular technological hubs, right? Now, each of these hubs will need a lot of people, be it people like CEOs, people like project manager, people like researchers, developers, engineers, and so on. So there is a whole lot of need or roles that are opening up across India. And with Amravati and Andhra Pradesh government with huge support, India is going to get its first quantum computer in less than 6 months. And that's the reason why we, moved this course to January, and we opened this course now, so that people can do this course, and then they can choose the next set of courses that they want to do, and get ready to be able to run utility scale or potentially quantum advantage circuits on the physical device when the device is here. Now, this and the Quantum Algorithm Center across the country, these two open a lot of new opportunities for India. Opportunities to fund your own startups, since governments are giving a lot of grants and there's a lot of VC funding flowing in. And of course, in the existing startups, there will be a lot of positions. If you see, 200 plus startups will be supported. So each of these startups will need a lot of people to run them. Then there are positions opening in academia, there are positions opening in the industry, there are positions opening in the NQM hubs, and and so on. This is a report by McKinsey where they say that the percentage of qualified quantum candidates is less than 33%. So a significant portion of this number of jobs that I showed you are going to be unfilled. So today, in this era of quantum utility, we need a focused workforce capable of discovering which problems in quantum computing are best suited to solve. Quantum computational scientists must be able to map these problems to quantum circuits. And tomorrow, as we realize our vision for quantum centric supercomputing, we'll need a much larger force capable of integrating advanced middleware that orchestrates cloud based quantum and classical computational resources. So, practitioners will need to be skilled in these capabilities to address domain and industry specific problems. And one another point that people keep asking is PhD is mandatory or not? So if you see PhD is green here, and for a lot of roles, PhD is not really required. So the preferred education or experience for new hires, it works very well with bachelors or even some amount of masters, right? But the only thing is that you should look at what kind of roles you are looking at based on your interest and advance yourself and do such courses, which there are multiple providers like NPTEL who have such courses. Skill yourself towards that role in the next few months or years. Now, in order to build this workforce, learning and enablement is key, and that's what we have been doing. So, we have been teaching a lot of classroom courses. In fact, in the last 4 runs of NPTEL, this particular course, we have taught around 37,000 students, and this course we have, 50 more than 50,000 students. And we have been prioritizing investing resources into advanced quantum education, building a diverse, quantum roadmap. Now, you have a lot of active research prototypes and collaborative skill building. There are a lot of technical working groups where researchers can be part of. For example, the Healthcare Life Science Working Group, which I am a part of. Then there is a working group in material sciences, high energy physics, sustainability, optimization, and so on. With NQM and AICT, the curriculum for quantum technologies, there's a BTech curriculum that was announced, and now there is a master's curriculum that has also been announced. And there is a lot of faculty development programs that are being run across the country to be able to reach that goal. I've put in a QR code of the IBM Quantum Learning platform. The platform is free. All the courses are freely available. You can do the course and you can go ahead and take the exam to get a badge if you want to. And these are all free. So all the learning modules and everything is to enable researchers to advance their utility scale experience explorations, and how you can help train your students to prepare for this quantum workforce. We have John Waters. He's a professor and he has been running this quantum education course. And there is also a Teach the Teacher series that has been planned, and so on. Right. So there are multiple ways. So for example, IBM Quantum Learning Platform that I showed you, we have typically every year we have an annual coding challenge, which we call the Quantum Challenge. There is Qiskit Global Summer School. You can also take in the Qiskit Developer Certification, which is a paid certification exam. But there is a lot of free content available on Qiskit YouTube channel, and of course you can become Qiskit advocates if you have already become a Qiskit developer or certified yourself with Qiskit developers. So there are a bunch of series that keep happening. So this is just for your information. So I mean, take this opportunity, skill yourself, do whatever it takes. But if you see that the career opportunities, there are a lot of opportunities, and there's very little people who are trained in this realm. So let's get skilled, let's learn more, let's continue this passion of learning, and let's create the future of quantum computing together. Thank you, everyone. See you in the next video.